video, let us discuss about the fully connected layer in backward pass. So this is something we should really understand what goes on under the hood when we use packages such as Keras or TensorFlow. So here you can see some gradients, right? Here you can see some gradients, and here this is a row vector, and size of this row vector is equal to the size of the output. So since the size of the output is 4, we have a row vector coming in from the next layer of size 1 cross 4. Okay, so our gradient of loss with respect to m, which is coming in from the next layer, right? So this is of size 1 cross 4, right? So this is of size 1 cross 4, and this is of Jacobian, right? And again, if you remember, the size of the Jacobian will be 4 cross 5. So the size of the numerator cross the size of the denominator. So this is 1 cross 4. This gets multiplied by 4 cross 5. So we, for the previous layer, what do we get? 1 cross 5. Why? Because the number of inputs is 5 elements in. Suppose there was a layer here, we have the gradient that will go inside this. So this is dou L by dou M here will be 1 cross 5, right? But there are two kinds of gradients. This is the gradient that we have to pass it to the previous layer, and we have to update the weights of the previous layer. But we also want to update the weights here into this W, right? And to do this, we will again use the chain rule. So we will have dou L by dou W equal to dou L by dou M into dou M by dou W. And this is really important to know. And so we want to take a step in the direction. So we want to find out this. What is this actually? Like if you do this, we will be getting dou L by W, right? So what is this? Dou L by dou M. So this is what we are getting it from here. That is 1 cross 4, right? So 1 cross 4. And what is this? Dou M by W, right? So this is actually the Jacobian. Now dou M by dou W is a Jacobian. And what is this Jacobian? This is a Jacobian of the output with respect to the weights, right? So we are able to compute this because we are able to differentiate. We were able to do all partial derivatives of M with respect to W. Why? Because we know exactly what is the function M with respect to W. So here we can see like M1 is equal to N1 into W11 plus up to M5 into W15, right? So we are thus able to compute this Jacobian. Why? Because it is of the size of M, which is 4, and the size of W, which is 20. We will look it in this way, more detail, right? So let's just have a look at it. So we have this dou L by dou M. So we have this dou L by dou M. What we want to compute? We have to compute dou M by dou N. And I'm claiming that this dou M by dou N is equal to W. Let us look at as it is true and if as now. So let's write down what M was. So M1 was, we have seen, right? So what was M1, right? So that's what we have seen. So M1 is equal to, what have we seen? Remember that, right? So N1 into W11, right? Up to N5 into W15 plus bias. So what would be our Jacobian dou M by dou NB, right? We know that Jacobian would be dou of M1 by dou of N1 into dou of M2 by dou N2, dou M1 by dou N3, right? So this is also 1, right? So this is how it goes till dou M1 by dou N5, right? So similarly, we will also get for dou M2 by dou N1 up to dou M2 by dou N5. And similarly, we will get for dou M3 by dou N1 up to dou N3, sorry, dou M3 by dou N5. So let me write it clear. So that would be really helpful to you. So what I'm saying is we get dou m1 by dou n1, dou m1 by dou n2, right? So dou m, so this is also m, right? So dou m1 by dou n3, dou m1 by dou n4, dou m1 by dou n5, right? So similarly, we have dou m2 by dou n1, right? So the next one will be dou m2 by dou n1. And the next one will be dou m3 by dou n1, right? Right, dou n1, right? So the next one, what do we have? Dou m4 by dou n1. So it is clear, right? So up to dou m4 by dou n5, right? So this is what we get. Clear now? So we will be getting bias also, right? So similarly, we will be getting for like how many are here actually? 2, 3, 4, 5, 5 cross 4. So totally it is 20, right? So this part is clear to you, right? So we have already written that dou m by dou n is equal to W, right? So that's what we are trying to find out now. Okay, so I hope this part is really clear to you now. So now let us look into the second element. Now we want to differentiate this m1 with respect to m2. So only n2 is a variable. Everything else is a constant. There is no n2 element. And when we differentiate n2, w12 with respect to n2, so we get w12. So now you can see the pattern develop, right? So now similarly, let's do one more, right? So let's do this term m1 by n3. So now we again differentiate, we find dou of m1 by dou of n3. So now everything but this term here with n3, so which is actually n3 w13 is what remains. So again, everything else goes to 0 and n3 goes to 1. So we get w13. And as you can see the pattern develop, we get all the way. And now let's simply do it for say the last layer. So now we want to differentiate say m4 with respect to n1. What happens when we differentiate m4 with respect to n1? Everything will go to 0 except the term. So we get w41, right? And similarly, we all get all the way to w45. Now this is actually the Jacobian of dou m by dou n. But it also happens to be the weight, and I'm claiming that Jacobian dou m by dou n is also equal to the weight. And this is why when you want to propagate the gradient to the previous layer, all we have to do is we want to multiply from the left. So so on the left, right? So this in our case a row vector of size 1 cross 4, and then we have so, right? And W is of size 4 cross 5. And all we do is we do a vector latex multiplication, right? So you can look into, you can look here, right? And this is the quantity, that is, this is the derivative of the loss with respect to output, because this term goes away. So this is the derivative of the loss, and this is what we propagate to the previous layer. So it is pretty simple if you invoke Jacobians, and in this case, it so happens that the Jacobian of the output with respect to the input is nothing but the weights. And when you want to propagate inputs to the previous layer, right, we simply multiply the gradient with the weights in the network, and this is what we propagate to the next layer. So we have done one bit of weights. Now we have to do the other bit, like we have to also find out the gradients with respect to the weights. You have done it, right? So we know what to propagate to the previous layer, but we still do not know how to update the weights in this layer. And now let's look at how to do that. So again, let me first write down the expression, because we will again invoke Jacobians, create the Jacobians of dou m by dou w. This time I will write it briefly. So we know that m1 is equal to n1 w11 plus up to n5 w15, right? So this is how we will be writing till m5 because we only have, sorry, M4, right? So because we have only four outputs, right? Plus, so this is how we will be writing. Hope this is clear to you, right? Okay, so why I'm writing this? Because we have to create the Jacobian now. Now, what will be the size of the Jacobian be? We know that the size of the Jacobian is the size of the numerator cross the size of the denominator. Size of the numerator is 4. The size of denominator is 20, right? So we have seen that, right? So the Jacobian that we will get is 4 cross 20. So 4 cross 20. So the size of this, because this is coming from the next layer. So we know that the size of this is 1 cross 4 and this is 4 cross 20. So in this case, we will call it the next grad, right? We will call it as the next grad. And so let's go on. The partial derivatives of the output of m with respect to the w in this layer. And if you are able to do this, we will be able to get dou L by dou W. We will know how to update the weights. So this is the derivative of the loss with respect to the weight. So if we have this quantity, we know which direction we have to change if you want to minimize the loss. If you want to minimize the loss, in which direction we can do that, right? So this is something we already know because this is coming in from the next layer. All we need to do this, right? So what will be the expression for this be? So we know that there are 4 rows and 20 columns. So what are those 20 columns? So first we will have dou m1 by dou w11, right? And then we will have all the way to, so you know that it doesn't change in the numerator. So then it will be dou m1 by the fifth by the 20th weight, which is dou, no? So the fourth, and so here we have 20, right? W11, W12, W13, 14 and 15, then W21, 22, 23, 24, 25, W31, W32, 33, 34, 35, 41, 42, 43, 44, 45. Clear? So totally we have 20. And similarly, what will the last row be? It will be dou M4 by dou W11. Clear? And then all the way to dou M4 by dou W45. So again, the size of this 4 cross 20, so now let's try to calculate these individual elements. So we are trying to populate the Jacobian by this, right? So as you can see, we are simply assigning the elements of the Jacobian to be some indexes of the input. So n is the input, and now see how is the Jacobian simply having. So let's compute dou m1 by dou w11. So what do we want is dou m1 by dou w11. So this is what we wanted, right? So everything will be a constant. Only this element under consideration will be non-zero. And again, we are differentiating it with respect to dou w11. So w11 will cancel and we will get only n1, right? So this will be uh, really important to understand, right? So this is how we will be getting for all the cases. So there is no element of 45 here, right? Simply let's take it as dou m1 by dou w12. So if we were to look at this element, the second one, this would be the second element here. So n1 into w12, right? So this one will be the second element, right? So how do we write dou m1 by dou m1 by dou w11, right? So how can I write that? Dou m1 by dou n1 into w11, right? So this is what we have seen, right? So if you just do it in the notebook, we will see that what we are doing exactly and what we are getting. So we get n1, n2, and we will keep on doing this till we get n3, n4, and n5, and then all the other 15 will be 0. Similarly, here we would we will get all the dou m1 by dou w1 up to the last cases, right? So if you want, let's simply do it for one of the elements of the second or second row. So what will be the second row like? So the second row will have elements of m2, right? So how can I write that now? So m2 is equal to n1 W21 plus N2 W22 plus N3 W33 plus N4, right? W44, we have till N5, right? So N5 W25 plus B2, very simple, right? This is how it goes on, right? So this is how we will be getting for everything. Now in this way, in this case, we have no elements of 1 in the first row. So the first 5 elements of this will be 0, like the first 5 elements, in the sense like we'll be differentiating it with respect to 2 1. So when we differentiate with respect to 2 1, so it will again be just n1, then we differentiate with respect to 2 2, right? With respect to 2 2. So the Jacobian, in simple terms, what I can say is like n1, n2 up to n5, right? Right. So this is how I can say, and then we will have n1, n2 into n3, right? And then n1 to n5, see, something like this, right? N1, n2 to n3, right? And then this is how we will be getting, right? So this is exactly what we are doing in this loop with the help of the Jacobian matrix. We are simply creating a Jacobian matrix. So what will be gradient? So what dou L by dou W will be? It will be simply multiplication of the next grad, the gradients coming from the layer, and this is dou by dou W, right? So which we just calculated as dou M by dou W. Here we call it by clear. So this is what we are doing here, and we know we can multiply this. Why? Because this is 1 cross 4, and this is 4 cross 20, right? So it gives us 20 elements. So these 20 elements are exactly the size of our weights. We have 20 elements in our weights, and once we have these 20 elements, we are able to use this to update our weights, right? So it is easy to use these 4 cross 5 matrix. So when we look at this reshaped version, we simply see that the gradients, what we need to update our weights. So once we have this, we are then able to update the weights in this layer. So we have done two things. We have created the weights that we need to pass to the pass to the gradients that we know. Also, we have the gradients that we need to update the weights. So these were the only two things that were needed for this layer. And once we have this, we can continue with the chain rule, and we are done for this layer. So this was all that we had to know about a fully connected layer. So just a recap, we first said that, okay, a fully connected layer is nothing but a weighted sum of all the inputs, weighted using weights in the layer. Right, then we looked at an example where we have the input, which is 5 numbers, and then we simply do a dot product with a W and add a bias to get our output. So this is a vector matrix. This is a matrix. This is a vector. So we multiply a vector on the right with a matrix, and then we added the bias, and with this we get the output. We get the output, which is of dimension 4 here. We then want to do the backward pass, and then we do the backward pass. We need two kinds of gradients. One is the gradient that we need to pass to the previous layer so that it can do with the chain rule, and one is the weight for immediate use, which we need to update the weight. One is the gradient to immediate use, which we need to update the weight in this layer. So gradient that going to the previous layer, and gradients which we use to update the weights in this current layer. So we then looked at how to do the two Jacobians. So one Jacobian turns out to be just equal to W, and the other Jacobian turns out to be this block matrix from, again, with nothing but the elements of input. And once we have this, we have everything that we need for this layer. Clear? So hope you understood this concept. Thank you.